Hello, welcome to Kerala MOOC's course page on digital signal processing. And today we are going to discuss with discrete time signals and systems. And you can refer through this book, John G. Prayaki's Digital Signal Processing Principles, Algorithms and Applications. And all these discussions are from sections 1.1 to 1.4 of this textbook. Now, what is a signal and what is a system is? A signal is normally we defined as any physical quantity that varies with time, space, or any other independent variables or variables. Mathematically, we describe a signal as a function of one or more independent variables. Say for example, in this case, here x of t is a cos 2 pi t, and here this x of t is depends it's a function of a variable t. So in this case, the value of x of t varies with respect to the variations in the time, and here also in this case x of m comma n is equal to m plus n whole square. Here also the value depends on. So we can say a signal is formally defined as a function of one or more variables which conveys an information on nature of physical phenomenon. Some of the examples of signals are one, it is electrical signal, either voltage signal or a current signal in a circuit. We can call it as an electrical signal which varies with the time. Another one, it is a acoustic signal, acoustic pressure or sound signal which varies over time. Mechanical signals, for example, velocity of a car over a time. Video signals, intensity level of a pixel over a time can also be represented as signals. Here we can see a speech signal is here, which contains the information over a short period of time, and it's a measure of amplitude, frequency and phase contained in a short interval of time. Here is another example for a signal. It's an ECG signal or electrocardiogram signal, which that signal provides a doctor with an information about the condition of the patient's heart. Similarly, you may have EEG or electroencephalogram. That signal provides the information about the activity of the brain. So all these signals, speech signals, electrocardiogram, electroencephalogram signals are examples of information bearing signals that involve as a function of a single independent variable. In all these cases, all these information depends on the single independent variable of time or t. Now what about this case? Here it is an image signal. Here in this case it's a this signal is it a signal? Yes, definitely it's a signal that's a function of two independent variables. So an image signal is an example for a signal with which is a function of two independent variables. The two independent variables, all these variables are some function, in this case are spatial coordinates. Let us say x and y coordinates. So see, if you can see here, it is here we in this point we used this one. Say for example, the intensity of the pixel at this point is represented as one signal, one information, and the intensity level of the pixel at this point is another one, it's another information. Now we can classify signal as in different ways. As you can see in this figure, signals With respect to the dimensionality, we can classify signal as one-dimensional signal or multi-dimensional signal. And with respect to the channel, we can classify it as a single channel signal or a multi-channel signal. Then depends on the value, it's a amplitude value, it's a continuous valued signal or a discrete valued signal. With respect to the time, continuous time signal and discrete time signal. And then depending on the periodicity, some signals are periodic signals and some signals are aperiodic if it does not satisfy the periodicity. Then depends on the way of expressing. Some signals are random and some signals are deterministic signals. And depends on the energy. Signals can be either is a power signal or some signals are energy signals. Then depends on the symmetry, we can classify signals as even signal and odd signal. And duration, impulse is a duration is a finite length signal and an infinite length signal. So there are a lot of we can classify signals in different ways. So coming on to the definition, signal is a function that conveys, it must convey any information. And now one way to understand the various types of, you may heard about analog signal. Analog signals are its amplitude is continuous, and it is continuous in amplitude and continuous in time. We can call it as an analog signal. If the signal is discrete in amplitude and continuous, you can call it as a continuous time signal. It's a continuous time signal. And whereas if the signal is continuous in amplitude but it is discrete in time, we can call it as a discrete time signal. And if it is amplitude is discrete and it is discrete in time, then we can call it as a digital signal. This is an easy way to differentiate what's the difference between an analog signal or a continuous time signal or a discrete time signal or a digital signal. So if you know this diagram or this representation, this block, then you can easily identify the differences. Now let us see continuous time versus a discrete time signal. So here it is a continuous time. These signals are continuous in time. Continuous in time means signal is defined for every value of time in a given interval of from A to B, where A is from -infinity to +infinity. For example, voltage as a function of time. So in this case, every time there will be a value at x of t. So we can call it as a continuous time signal. And here also there is a continuous values here. Continuous, it's a continuous value for every time t. So height as a function of pressure, number of position emissions as a function of time, all these are examples for a continuous time signal. Now let us look on the discrete time signal. And here the signal is defined only for a certain specific values of time, and typically taken to be equally spaced points in an interval. For example, number of stocks traded per day and average income per province. And all these examples say here it is signal is defined only for a certain specific interval of time. Now let us see the third one, that is continuous amplitude versus the discrete amplitude. And see here, the amplitude is continuous. In both cases the amplitude is continuous, and in this case the time is discrete but the amplitude is continuous. And here also the time is continuous, okay, and also but also the amplitude is also continuous. Now such type of signals we can call it as a continuous amplitude signals. Continuous amplitude signals, the signal amplitude takes on a spectrum of values within one or more interval. For example, color, temperature, pain level, everything is an example for a continuous amplitude signal. Now let us see the continuous amplitude, discrete amplitude. Here it is a discrete amplitude signal. The amplitude levels are discrete. Here these are discrete in amplitude. Amplitudes are discrete. And in the first case, in this picture, the amplitude is discrete, but the time is continuous. And in this case, the amplitude is discrete and the time is discrete. So examples are a digital image. It's an example for a discrete amplitude signal. And the population of a country. All these are some examples for a discrete amplitude signal. Okay, so we can define an analog signal as a continuous time. It is continuous in time and continuous in amplitude. This is continuous in amplitude and continuous in time. So we can call this signal as a analog signal. And a digital signal means it is discrete in time and discrete in amplitude. So we can call this signal as a digital signal. So in every digital signals are discrete in time and discrete in amplitude. And here it is an example for a continuous amplitude discrete time signal. And here it is an example for a discrete amplitude continuous time signal. So this is how we can differentiate these different different categories of signals. So we have an analog signals and digital signals. Analog signals are real world signals. All the real world signals are analog by nature, and they are fundamentally significant because we must interface with the real world, which is in analog in nature. But most of the cases we'll use digital signal processing systems. Digital signals are important because they facilitate the use of digital signal processing system, which will have practical performance advantages over several applications. We'll use digital signal processing systems. So if you are dealing with an analog signal, then you may have an analog system. If you are dealing with digital signals, then you may have digital systems. So an analog system means its input is analog and its output is again an analog signal. And there are a lot of advantages for an analog systems because it is easy to interface with the real world systems, and which do not need any conversion method like analog to digital conversion or digital to analog converters. Its speed is does not depend on the clock rate of the system. So in real world applications, we have almost all systems are in analog in nature. But why we use a digital system is, in the case of a digital system, the signal input is digital, output is again a digital, but it has a lot of advantages like reconfigurability in using the software. We can program it and we can rewrite the program, if you want any changes, then you can reuse or reconfigure the software, and you have a greater control over the accuracy and resolution of the systems. And lot of advantages for DSP processors like low sensitivity to component tolerance, temperature, low sensitivity to the temperature changes and aging effects, etc. That's why we use DSP processors in almost all applications. Okay, thank you.